Okay, good afternoon. So I'm going to be continuing the where we left off last lecture. So we were talking about multi-threading in a multiprocessor, and we talked about the overheads of having mutual exclusion in a multi-threaded application, and how that could create lock contention, which then could impact the performance of your application. Now, we talked about a couple of solutions to reduce the overhead of lock contention. For example, we talked about fine-grained locking. But let's say that you've done all of that and you still have problem. What should we do? So there are two locks that we can use that are designed specifically for multiprocessors. So the mutex that we talked about is not designed specifically for multiprocessors, and we'll see that. So these two locks are designed for multiprocessors. So the first one is MCS lock. So it's called based on the three scientists or three inventors of this lock. So this is a lock that is optimized for when a lock is contended on a multiprocessor. And then there is the RCU lock, which is read, copy, update lock. This is a lock that is very efficient if you have a lot of readers and some writers. But then the writers are very infrequent and the readers are very frequent, and you want the readers to access the data with no overhead. So then this lock is a good lock to be used in a multiprocessor system. Both of these two locks, the implementation of these two locks rely on atomic read, modify, write. So we're not going to talk about, disabling interrupts and those methods that we talked about for mutex. We're going to just stick with the read, modify, write instructions. So let's look at why the mutex implementation that we had is not is problematic in a multiprocessor. So here I have so this is very similar to the Spinlock. So this is the Spinlock kind of implementation that we saw. So it's just I'm rewriting it. But if you remember the Spinlock, it was with test and set, and we were passing a value. So this is very similar. So this basically is the Spinlock. And then I'm accessing I'm doing the rest of the function that I want to do. Now, what happens if everybody is using this as Spinlock? So what happens if this function is being used by, different threads? So now assume that you have a bunch of threads. All of them want to enter the critical section. Let's say this is the critical section. So basically, I'm sorry. So the critical section here is, I guess I have to make this similar to what you guys have seen so far. So this is a Spinlock. I have just, written it Spinlock.lock. So this is that line, and this guy is Spinlock.unlock. Just if you remember, so you can go back to the definitions that we had. So a Spinlock.unlock makes the lock free. A Spinlock.lock has this while test and set lock. And then this guy is the critical section. Basically, there is this value that we want to increment. So that's our function. At the beginning of the function, we lock the spin lock, then we increase the value, then we unlock the spin lock. So that's the setting. Now, what I'm asking is, how would be the performance of this code if multiple threads want to run this? So what's going to happen is this lock is a memory location, right? Now, if you're running this code from different CPUs, I want to remind you of what was happening under the hood with the cache coherence protocol. If you want to run test and set, you want to acquire this location in your cache in a modified state, because you want to read it and write it at the same time. So you want to get modify. Now, if all CPUs at the same time put get modify on the same bus, what's going to happen is they're going to be contending, they're going to be competing with each other to acquire this lock in modified state. And if you remember, there could be multiple messages being passed so that one of them eventually can acquire that lock. So there will be competition for different CPUs to be able to get this address in modified state. Now, so that's basically what this says. So they want to gain exclusive access to this memory location. In the MSI, if you remember, that exclusive access was given in modified state. In other protocols, it might have been E, but doesn't matter. So we know at this point that if you want to read and write to a memory location, you should be the only one. So the cache coherence protocol will sit there deciding who is going to be that exclusive writer. And if everybody is sending this request, there might be some competition. So this competition is going to slow everybody down. Now, you might say, OK, maybe I can make this competition a little bit easier by adding this here first. So modifying this is a modification of a Spinlock .lock. So this function, we're modifying this lock function. Instead of just doing test and set, I first do a read. So this one needs exclusive access. This one is just read only, right? So maybe I can just add a read first. First read this. If it is busy, then this becomes 1, and this while loop can continue. It doesn't need to run the second one. And I only run this second one if this one is 0, meaning that the lock is not busy. Then I try to get exclusive access. So maybe by doing this, I can make the competition less. So now not all threads would want to do test and set, right? This works when lock is busy, but the moment lock becomes free, so the moment one thread gets out of the critical section and makes the lock free, again, the competition is on. Again, now lock has become 0 for everyone, and everybody wants to acquire the lock in this in an exclusive state. So the competition will be on. And you know, if you remember, this is just really a busy waiting. Like they're just gonna acquire it in exclusive state, write 1 when it was 1, and then somebody else is going to get exclusive access, make it 1-1, and somebody else is going to require request exclusive access, make it 1-1. So it's kind of just pointless to have this. So this is a segue to do better. So let's do better. Instead of making them compete with each other, what we could do is we can make them wait on different flags. So instead of all of them waiting on this same lock, we can create or maintain a list of waiting threads. So whenever a thread comes and realizes that the lock is busy, so somebody else has locked it, it's going to add itself to a list of waiting threads, and then it's going to wait on its own flag. So if they're going to write, if they do test and set, we want them to do test and set on a variable that is local to them, that is not shared. And if we are able to do that, then there's no competition between threads to get exclusive access to the same memory location, because each one of them now is going to have its own variable. Now, so the idea is going to be, let's create this list of waiting threads and give each one of them their own variable so that they can wait on their own variable. And that would reduce the competition, and that would be good for the performance of our system. So here is how we're going to implement this. So we're going to design this class of MCS lock. And this class has a private member, which is a TCB. So this has to be implemented inside the Linux so that you have access to the TCB of threads. Now, we're going to create this pointer, which is the tail. And this is how we're going to maintain a list of waiting tasks. I've got a question. I will answer the question once I'm done with the implementation. So how are we going to do it? So let's implement the unlock. So one thing to note, this is not the only variable. Of course, this MCS lock has unlock, has all sorts of other things. This is the extra thing that we need on top of all the things that we've seen so far. So for unlock function, we're gonna, this is, if you remember, this is one of the instructions that we had, compare and swap. And it's getting an address in memory, which is this tail. This is the tail, the end of the list of waiting threads. It's gonna get my TCB, and it's gonna get null. So if you remember, compare and swap was getting an address and 2 registers. So what's going to happen is I'm going to, in this function, atomically, I check the tail with my TCB. Sorry, this is an unlock function. So this means that if I am the last person in the list, this means that nobody else is waiting, right? So if I'm the last person, basically, if tail is pointing to my TCB, then make the tail to be null. So atomically remove me from the linked list. So this atomically removes me from the list if I'm the only thread in there. So if I'm the only person, then just make the list empty because I'm done. I'm unlocking this. Otherwise, if I'm not the last one, if somebody else is also in this list, then, so somebody else is waiting, then I want to give them the lock. So I want them to now go. I will remove myself and let them go. So we're going to do this while to find the next person in the list. So I'm going to look at my TCB and then look at the next. So this assumes that in the TCB, we have this next element to maintain this list, right? The list of waiting threads. So you will see why there is a while here and not just my TCB next. The reason for this will be revealed when we look at the lock. But for now, let's say that my next could be null for a couple of times, even though this has returned unsuccess, meaning that even though that the tail was pointing to someone else, my next might still be null. And this happens because people are going to add themselves to the list, meaning that they're going to change the tail atomically. That happens atomically, but then they have to come and add themselves to me to create this linked list. And this is not atomic, so they can first add themselves to the list and get interrupted and not have a chance to add themselves to the next of the latest element. So therefore, you might check and see that the list has a tail, but the tail is not connected to you. So then you have to just wait for that to happen, right? Because you know that there is somebody else, but they haven't had a chance to add themselves to you. Because one of them was atomic, adding themselves to the queue was atomic, but adding themselves to you happens next step, and they could get interrupted in between. So we wait for that to happen. Eventually it will happen, and I will know who's next in the list from me. And once I know, I set their flag to true. So this is the flag that everybody is going to wait on. So everybody is going to have their own flag. That's why I'm saying this is me, this is the next person in the list, and this is their flag. I make their flag true. So I give them a signal that now you can go. Now let's look at the lock function. The lock function, let me clean this up. The lock function is going to atomically add itself to the end of the list. So this compare and swap gets the tail, gets the end of the list, and gets myself, and adds myself to the tail. So you can convince yourself that this while loop eventually adds my TCB to the end of the list. So once that happens, then I start waiting. So when I add myself to the end of the list, then I set my flag to false. And here is when I add myself to the end of the list, basically setting the next. These two are related, right? That's what I was saying. So this is a step one. Add yourself to the list by changing tail. Here, add yourself to the last TCB in the list. So once you change the tail, now go ahead and add yourself to the next of the last element in the set before you add yourself. And then once that's done, then start waiting. And you can now see that I'm just waiting on my own flag. I'm not waiting on that shared lock. This MC, this, oops. My apologies. So this is, I'm adding myself to, so I'm waiting on my own flag. I'm not waiting on somebody on this shared lock. And finally, let's look at how this shows up itself in the performance. So this is basically the original Spinlock. This is modified Spinlock. And this is the MCS lock. So on the y-axis, I have the time that it takes to execute critical section. And on the x-axis, I have the number of processors. Now, as you can see, with the Spinlock, the time that it takes to execute the critical section goes up as the number of processors go up. So the more threads you have, the more time it takes for each one of them to execute their critical section. And this is because of the overhead of accessing this shared lock. When we modified it, it's a little bit better because most of the time they're just acquiring that location as read-only. But every time the lock is freed, then everybody wants to get it as shared. So it's still bad. And with MCS, as you can see, the overhead is basically constant. So as you add more and more cores, the overhead is not going to increase. So the overhead kind of stays the same. So the time to execute the critical section doesn't change. Oh, somebody is asking about this memory barrier. So this memory barrier here is to make sure that we don't reorder instructions. So I want this instruction to happen first and then this instruction to happen. So I put a memory barrier here to make sure that there is no reordering between my instructions. So that's why there is a memory barrier, because again, you don't want this instruction here is independent than this instruction. So the compiler could decide to reorder them, or the hardware might want to reorder them. So you don't want this reordering to happen. You first want the flag to become false, and then add yourself to the old tail, to the person before you. That's why you put that memory barrier. You could see that if you first add yourself and then make the flag false, something bad could happen, because then the other person might see you here, that they see that their next is not null. So they see that you are there, and then they could make your flag true, but then you run and you make your flag false. So that's bad. That's why you first want to make it false and then add yourself to the person before you, so that when they release, they make it true, and then you can just go. Here is when you're waiting for your flag to become true, and your flag becomes true whenever the person before you releases the lock. Okay, let me answer the questions. So if you test and set on local variables, is that still cache coherent? No, because if you have your own variable, if each thread has its own variable, then you still send this shared get modify, for example, but the advantage is that you're the only one who needs this location. So other cores are not going to send get m for the same address. So there's no competition. You're still talking to the cache coherency protocol, but because other threads running on other processors don't need this variable, you're the only one who does this get m. So you don't need to interact with others. So that's the benefit of it. Then the question is, while next equals null, isn't this busy waiting? Will there be a context switching there? I assume you're talking about this guy. This is busy waiting, but it's going to be a short busy waiting, right? It's going to be short because it's going to be just a matter of these 3 instructions happening. So you're not going to busy wait for as long as, you know, like 1 minute or 2 minutes. You're going to busy wait for a couple of instructions until somebody adds themselves to the to you, and that happens very fast. So if you remember, I made this comment that busy waiting is kind of like unavoidable. We just want to make it as short as possible. And in this instance, as you can see, you're busy waiting until the other thread. So first this happens, the other thread adds themselves to the tail. So that's where you come to this else, right? You check the tail and you see that somebody else is there. Now, they haven't had a chance to add themselves to you yet. So you busy wait until that happens. But how long is it going to take for them to add themselves to you? Well, it's going to take a little number of instructions, right? So it's going to be okay. So it's just you're going to busy wait for some number of cycles until they add themselves to you. Then you can just get out of this busy waiting. Good question. The other question I have is, where are you setting lock in unlock? Right, there is no lock anymore in this one. So we got rid of this shared lock. So now everybody has their MCS flag. So we're just playing with this flag. So whenever you come and you see that somebody is in the list, you add yourself to the back of the list and you start waiting on your flag. Whenever you're done, you just set the flag for the next person to true and let them go. Right. And by the way, if you're the only person, so let's say you're the only person who calls the lock. So let's say lock is free and you call lock. You add yourself to the list, but then all the tail is null, so you don't wait. So you get out of here. So you start running. So you don't wait. So this next part happens only if you are not the only person on the list. So if you are not the only person on the list, it means that you have to wait. Somebody else has, the ones before you, one of them has the lock. Publish, good. Now let's talk about the second lock, which is RCU lock. So this should be actually really important to you. So if you end up in your career writing a multi-threaded application and you find yourself that your threads have critical section, and this critical section is big and there is locked contention, the first thing you have to think about is, why is this happening? Can I make a better design choice to avoid this lock contention? And there you should think about, basically fine-grained locking, maybe switch to lock-free. Basically go through all these suggestions here first. Can you do fine-grained locking? Can you do per processor data structures? Can you actually have a staged architecture? So that should be your first option. Now, if none of these apply to you and you can't use them and you still have a problem, then maybe look at MCS and see if you can use MCS. For the project that we were doing with my grad student, we actually looked at MCS, but we ended up not needing it. There are some implementation of MCS. And this RCU, if I'm not mistaken, Facebook has a library for it. If I'm not mistaken, I think Facebook has a C library for RCU, because we also got to look at this as well. So there are implementations of these. I believe this one is implemented inside Linux, and this one had a library from Facebook, open source, that you could use. So let's look at the second one, MCU. For this, for RCU, I'm not gonna explain the implementation. I'm gonna just tell you what it is and under what circumstances you should be using it. So this one, the goal for this is to have readers access shared data with zero overhead. So if you have a bunch of readers, let's say, for example, this makes sense for Facebook, for Amazon, for Google. You have these databases, right? And people are querying your databases. And most of the queries are read queries. They want to read. And these are very important for you to answer these queries with zero overhead. You don't want to wait. You don't want anything. You just want to access the database, read whatever you want to read, and have an answer. So then RCU is your lock. Now, in this lock, writers are in disadvantage. If you remember the writers lock that I explained during the tutorial, in that implementation, writers had higher priority over readers. So whenever the writer comes, they would, starve every readers. In this one, we're going to give more priority to the readers. We want our readers to be fast. Writers could take time. So readers are going to access the database without acquiring the lock. So they don't need to acquire any lock. It's lock free. They can just go and read the database. Writers, however, when they want to access the data, when they want to write, they're going to go through this process. They're going to make a copy of the database. So they want to make a change. So they take a copy of the current state of the database. Then they start modifying their own copy. So they work with their local copy that they made. Once it's all done, then they change the database. And this change has to happen atomically with just a single write. So usually this happens by pointers. So usually your database should have a pointer to the current version. And then when the writer wants to write, they just change that pointer to now point to their copy. So that's why they made a copy, they changed the copy, and then they changed the pointer to point to their copy. So this is the only restriction, that the write should just be changing a single pointer in an atomic instruction, because you can just change the pointer atomically. But if you're going to go ahead and write a bunch of stuff, it's not going to work with this one. So with this, you want to call it downside, you want to call it it's not a downside, but it's an artifact of this design that we have. We're allowing multiple copies of the data to exist at the same time. As you can see, right? The writer is going to get a copy, change the copy, and then change the pointer. Now, when the writer changes the pointer, there still might be some readers that are using the old data. So here is the whole picture altogether. So with this one, we need the scheduler to help us for housekeeping. Let's see how. So this is time on the x-axis. Let's say a writer comes at this point. So here is when the writer comes, they make a copy, they change it here. So they have changed their own copy. And at this point, they want to publish their copy. So this becomes the time that the update is published. Now, if I had readers that came before the data was published, they're going to be using the old data. Even though the writer was changing its own data, the readers didn't have any access to that data because it was local to the writer. So they're using the old data. They're reading the old data. Now, if I have a reader that has started before this data was published, there is no guarantee. So if a reader comes after a writer comes, we don't have any guarantee which data this reader is going to see. It could see the old data, it could see the new data. But if a reader comes after the data is published, then they will definitely see the new data. Now, if we have this like long read that happens before the publication of the data, then when this last read ends, this is where we need the scheduler to help us, because the scheduler knows all the reads when they happened. So when the last read happens, so the last read that started after the writer started, but before the writer published its changes, so these reads, at that point, when the last one ends, it's the grace period end. So at this point, we need garbage collection. So at this point, there is not going to be any thread that needs the old data, because everybody that comes after this publication, they're going to see the new data. And these guys that started before the publication, last one of them is done. So I don't need the old data anymore. So I can garbage collect the old data. And from now on, so we're going to delete the old data, and everything after this, they're going to just definitely read the new data. Okay, so this is RCU. Now you have to be careful about this, right? Because this brings inconsistency, and I bet you have seen this inconsistency in platforms like Facebook. So you look at a post today and it has 100 likes, and then in an hour you look at it, it has 50 likes. So it has gone down. It's because there's inconsistency. There are a bunch of, but there are different copies of the data that you're accessing, and that's why it's happening. Okay, so you have to be careful again with this one. So your system should be resilient to reading different things, different versions of the data, and that should be okay with you, right? If you always want the most up-to-date version, then RCU is not your option. Okay, so I have a question. Can you push a new version while a read is in progress? Yes. So as you can see, this read is in progress, and it actually might be using the old data. And then here you publish the new data. Now at this point, I have two versions of the data. And that's where I need the scheduler to tell me when this ends so that I can garbage collect. Okay, so just a few points about RCU. In this one, readers in this one, the readers don't need to lock. anything, right? So they don't need to lock. Here is something about disabling interrupts on entry. So this is for systems where you want to give readers utmost priority. You make them disable interrupts so that they don't get interrupted, so that they can finish as fast as possible, right? Because it's important for your readers to finish. If you have really long readers, again, RCU is not your choice. This will work for systems like Facebook, Microsoft, like the web search, things that you have queries that take nanosecond or microsecond to finish. So you're going to just read something really quick and that's it. So you want to give your readers utmost priority, the highest priority. So they go in, you disable interrupts so that the reader doesn't get interrupted. It can finish whatever it wants to read as fast as possible. But then the readers don't need to lock anything. They just go in and read whatever they want to read. The writers, however, they need to acquire the write lock. They need to create a new copy. They need to publish their new version with an atomic instruction. So they need to first make all the changes and then atomically change a pointer to release their updates, and then they can release the write lock. So these guys have to acquire the lock because we don't want multiple writers. We want a single writer. So every writer acquires the lock before making changes. And then you garbage collect once the scheduler sees that all the the readers that might have access to the old data are done. So this is like just high level implementation. We're not going to go to the details. The detailed implementation of this, I believe, is available in your book. So I'm not going to, in the exam, we're not going to ask you about the detailed information or detailed implementation, but you're going to be asked about the overall design. So whatever we talked about is on the table. Whatever is not in the slides is not going to be asked. Can you have two writers simultaneously? I actually answered that, right? No, because they have to acquire the write lock. Okay, so I'm going to end this lectures with talking about scheduling multiprocessors. So now that we know, so again, let me tell you where we are. We started this in the previous lecture. We started with looking at how the architecture of a multiprocessor is different from a uniprocessor. And then next we saw how that could affect us in terms of the performance. And we looked at a single case of lock contention. And we saw how this having multiple caches could impact us. Now, I'm going to end this lecture by talking about what the operating system can do in terms of scheduling threads on multiple processors. One naive way is to just have a single scheduler, as we had it in uniprocessor. So have a single scheduler with a single ready queue, and this scheduler will schedule tasks on all the CPUs. So what that means is, you maintain a single ready queue. Now, on each CPU, whenever an event happens, either a system call or an exception or an interrupt, each CPU starts running the scheduler code. So we have this scheduler class. They start running the code for that. And that scheduler class has a single ready queue. So all CPUs would be dequeuing threads from this single ready queue. So this is the naive approach. Basically, we're not going to change anything from from uniprocessor, we're going to now run the code on different CPUs. So any problem with this? Well, it's going to be, we're going to have lock contention, right? The exact same issue that we talked about so far, about lock contention. Now I have this single data structure, this ready queue, and this should have a lock because it might be simultaneously accessed from different CPUs. Now, if I have like, 256 CPUs, they're going to contend for locking this guy to basically dequeue tasks. And that is very, very bad. No matter what kind of lock you use for this, even if you use those locks that we talked about, it's going to still have high impact on your performance, especially as the number of CPUs go up. So we're not going to do this. A better implementation or an alternative is to have different ready queues for different CPUs. This is kind of like if I go back, it's kind of like per CPU data structure. If you remember, one of the ways to improve the performance of your multi-threaded application was having per CPU data structure. This is an example of that. So we're having per CPU ready queue. So each CPU is going to have its own ready queue. Now, something that came to my mind, I don't know if anybody has done it. Maybe a hybrid of these two would be nice. So I know that this is done right now in Linux. So Linux is doing this. There has been some designs for this. I'll talk about it. Brainfuck, I think, did this. But then it's deprecated. Nobody is using it. But maybe a hybrid of this might work. Maybe you could have a single ready queue for 2 or 3 or 4 CPUs, not for all CPUs. But anyhow, so it just came to my mind. Maybe somebody can do some research on that, see if it is good, or maybe others have done it already. I don't know. Anyhow, so now this is good. There is no lock contention with this one, but there is a problem of load balancing now, because as you can see, for example, the example I'm showing right now on the slide, CPU 1 has 3 threads. CPU 2 has empty ready queue. Now, CPU 1 right now is busy, but CPU 2 is idle. And CPU 4 has like 4 tasks. So if I'm going to do this, then somehow I need to load balance between these queues. The other thing is, what if I have priorities, right? Do I also want to consider those priorities in my load balancing? Let's say if all these tasks here, T1, T2, and T3 are high priority, and all the tasks here are low priority, then what's going to happen in my system is that I have a high priority task who is waiting, and I have a low priority task that is running. That's bad, right? So if I look at overall system, I see that I have these high priority tasks that I would prefer to run now instead of this low priority task here. So it's going to be bad both in load balancing and also with priorities. So having these separate queues. So somehow, first of all, I need to load balance in terms of the number of threads in each queue, but also kind of load balance in terms of priorities. So now we'll see how this is going to be extremely difficult. You might think that this is easy to do. You'll soon see how difficult this is. Okay. Now, in order for you to load balance, you need to have a metric for load. What is load? As I mentioned, option 1 is to just look at the number of threads. How many threads are waiting? And the difficulty with this is that you're going to ignore priorities. So what the situation that I described in the previous slide is going to happen. You might have 4 threads in all CPUs, but then maybe one of them, all 4 are low priority, and all 4 are high priority, and that's bad. So second option is kind of to weight the number by the priority, right? Maybe I can now make sure that the load is balanced in terms of the multiplication of the number of threads and their weight. So for example, this is an example. Let's say one queue has 1 thread with weight 9. Let's say the more your weight is, the higher your priority is. And let's say another queue has 9 threads with weight 1. Now, if I do that multiplication, 1 times 9 is equal to 9 times 1. But in reality, this is a bad situation if I have. So if I put only 1 thread in one queue, even though the weight was 9, and 9 threads in another queue, now if this high priority goes for I/O, now CPU 1 becomes idle, whereas CPU 2 has now 9 tasks or 9 threads competing for the CPU. So that's bad. So option 3, which is the option that is used in Linux, does use these weights, but also considers the CPU utilization. So it also looks at how much CPU each thread uses. So even if your weight is high, but you're going to for I/O a lot, then this should bring down sort of the load on this CPU. So the load metrics, the load metric in Linux considers the number, their priority, and how much CPU time each one needs, and uses the whole 3 variables to calculate the load metric. There is this one that I'm mentioning here because I need it later. In Linux, there is this auto grouping that happens, and auto grouping, basically what it is it puts each new thread, gives each new thread the same priority that its parent thread or parent process had. So if you initiate a process with weight 9, let's say this is a priority, we give it priority 9, and this thread creates another thread, they both get the same priority, but within the same process. And we'll see how this impacts, because we're gonna divide. We're gonna have per process weights rather than per thread weight. So we don't want a situation where one process creates 100 threads and each thread gets the same treatment as each other, because then all processes would have incentives to create more threads to get more CPU. So if we have a process that has 100 threads, we kind of want to ignore the number of threads that this process has and treat them all as a single unit. So we'll talk about that later. So I'm going to end this today's meeting here. So in the next lecture, we'll talk about we'll continue with load balancing. I was hoping to finish these lectures this time, but unfortunately it didn't happen. And I was under the impression that our makeup sessions are as long as the sessions, like 1 hour and 20 minutes, but then I realized that they're not. So probably I'm going to add another makeup session in the next half of the term. So we already have one scheduled after the reading week, I will add another one to cover the 2 sessions that were missing during the midterm week. Okay, so with that, I'm going to end today's lecture. Thank you for attending and asking good questions. I hope you all have good midterm week, and see you after the reading week. Bye-bye.